Hi, I'm Samit, a third year BSMS physics student at IIT Roorkee, and this is my presentation on the project Potato Disease Classification for the course PSC 351 Fundamentals of AI/ML. I chose this problem because potato is a major food crop worldwide, but it suffers from fungal diseases like early blight and late blight that can cause huge yield losses if not detected in time. Traditionally, farmers detect these diseases manually by visually inspecting the leaves. However, this method is time consuming, depends on human expertise, and is often inaccurate in the early stages. So, to solve this, I made a deep learning model that automatically detects and classifies potato leaves as healthy, early blight, or late blight, using only an image of a leaf. This would help to detect diseases early, allowing timely treatment and reduce crop loss and increase productivity. Now, before I move on to the code, I would like to explain some topics that would help us understand the code better. So let's start with artificial neural networks. In order to explain this, I'll be using an example. Let's suppose we have a classroom where A to G are the students, and these students don't yet know what a lion looks like. We also have a teacher H who knows what a lion looks like. Now, each of these students are given a particular task, and that task is to identify a specific part of a lion's body. For example, the task of A is to identify the eyes, task of B is to identify the mouth, task of C is to identify the body, D is to identify the legs. Each of these students can give a score. This score can range from 0 to 1, where 0 means that that student does not know whether the image is of eye or not, and 1 means the student can surely say that the image is of an eye of the tiger. Now, this A, B, C, and D send information to E and F respectively, where E multiplies the information sent by A with a suitable weight. It sets him a score that I believe I can say with 50% or 60% certainty that these are the eyes of a lion. Where what E does, E gets information from both A and B and multiplies it with a weight. Why do we multiply it with a weight? We multiply it with a weight because the weights tell us how important a particular feature is. Some features are more important than others while detecting images. So, for example, here the facial structure is more important than the feet. Therefore, this will have higher importance. Hence, this will have more weightage. Therefore, we multiply it with weights. Now, the part of E is to identify the upper half and F is to identify the lower half and send information to G. G again multiplies these by weights and finally makes a prediction. Now, G can make either yes or no. G can say that this is image of a lion or this is not an image of a lion. Let's suppose that G makes a false prediction. But we also know that the teacher knows that this is an image of a lion. So it will tell G that we have made a wrong prediction. G will then send this information to E and F when the information he got was wrong. This will go again to A, B, C, and D. And then these students will make some changes so that when the next iteration comes, when the next time an image is given to them, they make a better prediction. And this is the basis of artificial neural network. Now let us understand with a simple example. Suppose we have a 200 cross 200 pixel image. Then total number of pixels will be 40,000. Now each of these pixels is given to a neuron, and each of these neurons is connected to a neuron on the hidden layer. This neuron has one specific feature, and that these neurons have one specific purpose, and that is to extract the feature, extract a particular feature. Each neuron is responsible to extract a particular feature out of our image. What happens is that in this neuron, we get the value x1, x2, x3 up to x 40,000. Each of these values are multiplied by the weight. So x1 is multiplied by w1, x2 is multiplied by w2, and so on. And then an activation function is applied. And after the processing of the activation function, the result further goes to the next hidden layer. And then the result goes to the output layer where final decision is made, where the final decision is made. Now, this uh, this prediction can be true or can be false. And the difference, how much our predicted value varies from the true value, is calculated using a loss function. When this is given to the optimizer, the main goal of optimizer is to reduce the loss function, is to make our prediction more close to the true value. The optimizer then helps us to change the weights, to modify the weights in such a way that the prediction becomes smoother and more accurate. Now, this one complete cycle of forward propagation and backward propagation is called an epoch. And in our presentation, I have used 10 epochs. That is, my forward propagation and propagation happens 10 times on the entire data set. Now, the problem with this approach is suppose we have a very large image size of 1920 cross 1080 pixels. Then what will happen? The first layer of neurons will be approximately 6 million and the hidden layers will be approximately 4 million, which is highly, which requires very high computation and it is difficult for us. So what we can do is we can use CNN. CNN is convolutional neural network in it is a deep learning model specialized for grid structure like images. It uses convolutional layers to make predictions. What happens is that it has several layers within it. Thus, what happens, let's understand this example. Here we have an image. Then we choose kernel. This kernel moves over the entire images and moves over the entire image and we perform convolution. And then after the convolution, when the features are extracted, we then do pooling. Pooling further reduces the dimensions, and once we have got to this stage, we flatten this into a 1D array and then connect it to the ANN. And I have already explained what ANN means with the example of the lion. Now, let's see what the kernel actually does and what convolution does. So this is our images. This is our image represented by numbers. Here we have our kernel. This kernel moves over the image and we perform multiplication of each cell. So 9 is multiplied by 0, then it is added to 4 into 2, then it is added to 1 into 1, then added to 1 into 4, 1 into 1, 1 into 0, 1 into 2, 1 into 1, 1 into 2 into 0, and 1 into 1. All these are added and we get 60. Now, this kernel now shifts one place and now it will overlap this region. Again, cell by cell multiplication will be done and final result will be written here. Again, our kernel will shift, cell by cell multiplication will be done, result will be here. This will be done for the entire image and after that we'll get a grid and this grid is the feature map. What a feature map does is feature map holds important features of an image. This entire role of this filter is to extract important feature out of our image. And each kernel is responsible to extract one feature out of our image. I hope that is clear. Now, pooling further reduces the image dimensions. Suppose we have a feature map of 4 cross 4. We divide it into 2 cross 2 grids. Now each 2 cross 2 grid is replaced by the maximum value present there and this is called max pooling. And when we replace it by the average value, it is called average pooling. The main idea of pooling is to maintain the feature and reduce the processing that is required, that is reduce the image size. Now, what are the benefits? The benefits of using this, parameter sharing, sparsity of connections, and translation equivariance. Now, since we have all this knowledge, now we can move on to the code. So let's see the code. Okay, this is our code. The first step to make a model is to collect data. And in order to collect data, I have used Toggle and I have used this data set plant village. This plant village has several files of different plants. But for our project, I have used potato early blight, potato late blight, and potato healthy blight. First, we load this data. First, we load this data into our code, and then we make all the images uniform. We want that all the images should be of the same size. Also, we want to define batches. Why we want to define batches? Suppose we have thousands of images, and in order to read all the thousand images at the same time will be difficult, and performing computation over it will also be difficult. So what we can do is instead of taking all the thousand images, we can take 10 images, then again 10 images, then again 10 images, and it would help us do the processing in a better manner. Now, once we have got this, once we have defined the image size, once we have defined the batch size, we need to load the data. Uh, once we have defined the image size, once we have defined the batch size, now what we'll do is we'll split the data into two parts. One part will be used to train the model, and another part will be used to validate the model that our training has been successful or not. So here, 80% of the data is used for training, and 20% of the data is used for validation. Now, since we have loaded the data, uh, we made the data uniform. Now we want to visualize whether the images are being loaded correctly or not. So out of all the batches we have, I have taken out one batch. I have taken out one batch, and since each batch has 32 images, I have taken 9 images out of that 32 images and plot them along with their class names. So we can see that here. This this image belongs to potato late blight. This belongs to potato early blight. So we can see that the data has been successfully loaded. Now what we need to do, we need to create our model, train our model, and evaluate our model. Also, while creating the model, I have used data augmentation. What data augmentation does is, suppose we have this image. Now, I can rotate the image by some degree. I can flip the image horizontally or vertically. I can increase or decrease the brightness. I can zoom in or zoom out, and all these operations will create new data for our model to learn from. And this is what is happening in data optimization. Here I have flipped the image, I have done random rotation, and I have also done random zoom. I hope that's clear. Now, I've already explained what optimizer is, what loss is, and what matrix you should use in order to compile it. Now, here we can start model training. As told earlier, I have used 10 epoches. How many epoches? 10 epoches. Now, we have stored all the models' accuracy and losses from the training history in this part. And then, using the training history, we can plot accuracy and loss. What accuracy and loss plot shows us that in the accuracy plot, both the accuracy of the training and accuracy of validation should increase with the number of epoches. And for loss, both both the loss for training and the loss for validation should decrease with the number of epoches. We can see it as I've already run this, and here we can see that model performance over time with training and validation accuracy increases with the number of approaches, and the training and validation loss decreases with the number of approaches. We can also see that I have used different ratios in order to show how my model is working, and I have also made a confusion matrix in order to represent the efficiency of our model. So, why do we use this confusion matrix and why do we use these ratios? I'll explain to you uh, later in this video. Also, once I have got these graphs, I've also used, once we get these graphs and we got the confusion matrix and the ratios, we use the validation data to check whether our model has been correctly trained or not. So again, we do the same thing. We take one of the batches, and then we use it to test whether our data is correct, whether our model is giving correct predictions or not. We have taken 9 images, and the model has to correctly predict all the 9 images. We can see here that we can see here that the model is acting quite right. The actual photo is of late light and the predicted is also of late light. The actual image is of early light and the predicted is also early light. You can see that the model has given correct output for all the 9 images. Hence, we can say that the model is performing well. Now, let us also understand this confusion matrix and these ratios over here. So, confusion matrix is a table used to evaluate the performance of a classification model. On the right side, we have the actual process, the actual values that are present there. And here we have the predicted classes, the values that are predicted by our model. Let's say the actual value is positive and the model also predicts positive to end up with true positive. In here, the model gives a false value whereas the actual value is the true value, so we get false negative. Here, the actual value is negative, but the model predicts positive value. Here, the actual value is negative, but the model predicts negative value. So, with the help of these, we can calculate these ratios, that is, sensitivity, accuracy, negative, predictive values, precision. Now, let's understand these ratios. Accuracy shows us how many total predictions are correct. Precision shows us out of all predicted positives how many were actually positive. Recall shows us out of all actual positives how many did the model correctly find. And F1 score shows the harmonic mean of precision and recall. Now, uh, since we have already seen that the model works quite well, we can see that after each approach, our model's accuracy is also increasing. We can also see from here that our precision is quite good, our recall is also good, and F1 score is also good. Also, in the confusion matrix on the left side, we have the real labels, and here we have the predicted labels, and we can see that our model is giving correct input. That is, the actual label and the predicted label match for most of the images. Here also the actual label matches for most of the images. Now, since we have already trained the model, we have checked the model on validation. Now we'll upload a random image, and see whether the model predicts correctly or not. So here I have used a file named test file, which is of potato early blight, and I have uploaded here. And now when I run this, I got the model predicts this image is most likely potato early blight. Hence, we can say that our model is working beautifully. And that's all for our presentation. Thank you so much for joining. Thank you.